In 1971, two physicists boarded commercial airplanes carrying atomic clocks and flew around the world. And when they landed, those clocks disagreed with identical clocks that had stayed on the ground the entire time. Not because something failed, because something worked exactly as Albert Einstein had predicted 66 years earlier, when he calculated the time would pass at different rates depending on how fast you moved through space. Most people hear that and file it away as a physics curiosity, something true but distant, like the rings of Saturn or the temperature of the sun's core. And that is where the misunderstanding begins. What Einstein described was not a quirk confined to laboratories or spacecraft. It shapes every moment of your existence. It governs the technology you use every single day. And once you really sit with what it means, the idea of time as a steady, reliable current carrying everyone forward at the same pace falls apart completely. You think you know what time is. You have lived inside it your entire life, glancing at clocks, feeling afternoons drain away, remembering yesterday and bracing for tomorrow. And the whole experience feels so immediate and familiar that the question seems almost insulting. But here is the challenge. Define it. Not describe it, not gesture toward it with words like flow or passage, but actually define what time is, the way you could define water or gravity or heat. Augustine of Hippo arrived at the same wall 15 centuries ago and put it plainly, writing that when nobody asked him, he knew. But the moment someone wanted an explanation, the knowing disappeared. And yet here we all are, scheduling our lives around a thing we cannot define, mourning its passage, measuring it down to the millisecond, completely certain we understand it, and never once stopping to question whether that certainty is earned. That certainty is the first mistake, and it runs deeper than most people realize. When you follow the question of what time actually is, all the way back through physics and philosophy and geology and cosmology, you arrive at something that does not just correct a misunderstanding. It changes the shape of everything you thought you knew about reality, about your place in the universe, and about what it means to exist at all. Here is the picture most of us carry around without ever examining it. Time flows forward like a river, from past into future, carrying everyone along at the same steady pace, regardless of where they are or how fast they are moving. The present sits at the edge of that flow, a thin, illuminated line between what has already happened and what has not happened yet. And the rate of that flow, everyone has always assumed, is constant everywhere, for everyone, at all times. That picture is wrong in ways so deep and so far outside ordinary human intuition that even Einstein paused when he worked through the mathematics. Before getting to him, though, there is something you can confirm yourself on any clear night that already breaks the common picture wide open. Go outside and find Rigel, the blue giant anchoring the constellation Orion, and understand what you are actually seeing when you look at it. The light entering your eye right now left that star around the year 1160, traveling 186,000 miles per second across 860 years of distance, arriving at your retina while Genghis Khan was still a generation away from being born and the Crusades were actively underway. You are not observing Rigel as it exists. You are observing a fossil of light from a world that has since had centuries to change. And that is just one star. The Andromeda Galaxy, cataloged by astronomers as Messier 31 and faintly visible to the naked eye on a dark night, sends us light that spent 2.5 million years in transit before reaching us, meaning the image we see dates from a time when Homo sapiens had not yet arrived on this planet and our ancestors were still learning to work stone. Every point of light in the night sky represents a different moment in the past. All of them arriving simultaneously at your eye, assembled into what looks like a single present moment, but is actually a mosaic cut from thousands of different eras. There is no universal now in a universe where light travels fast, but not instantly, and where every observation is therefore a form of looking backward. Every time you watch the sky, you are doing archaeology. The discovery of deep time, the recognition that the Earth and the cosmos are not thousands of years old, but billions, came not from a telescope, but from the ground itself. James Hutton reached that understanding, standing at Sicker Point on the Scottish coast in 1788, staring at layers of ancient sandstone tilted at violent angles beneath younger horizontal rock above them. Those tilted layers had been deposited by water, grain by grain, compressed over ages into stone, then fractured and upended by geological force, then eroded down, then buried beneath new sediment laid by a completely different era, the whole cycle repeated not once but many times over, each repetition requiring spans of time that the human nervous system has no natural framework to hold. Hutton looked at the cliff face and concluded he could find no sign of a beginning and no prospect of an end, and his contemporaries did not celebrate him for it. They recoiled because deep time is not merely an intellectual revision. It is a psychological confrontation with how brief you are, and that confrontation produces resistance in almost everyone who genuinely faces it. What the physicists and cosmologists who followed him established is that the universe itself is approximately 13.8 billion years old, that Earth formed from the debris of earlier stars about 4.5 billion years ago, that the first life appeared here perhaps 3.5 billion years ago, and that all of multicellular life, everything visible without a microscope, is perhaps 600 million years old. The dinosaurs alone ruled this planet for 160 million years. Our own species has existed for around 300,000. To feel those numbers rather than just recite them, imagine the entire history of the universe compressed into a single calendar year, with the Big Bang igniting at midnight on January 1st and every month representing just over a billion years. On that calendar, the Milky Way forms in mid-March, the sun ignites on September 9th, and Earth solidifies 4 days later. The first living organisms appear around September 25th, but nothing you could see with your eye shows up until mid-December. Fish appear on the 19th of that month. Dinosaurs arrive on Christmas Eve and vanish in an asteroid's aftermath on December 29th. And the first tool-using hominids walk onto the scene on New Year's Eve at around 10:30 in the evening. Every war, every invention, every empire, every poem, every act of deliberate cruelty or extraordinary compassion in the entire recorded history of human civilization fits inside the final 10 seconds before midnight. 10 seconds out of a year. Newton's model of time felt so self-evident for so long, not because Newton was careless or limited, but because the universe turns out to be structured in ways that actively violate the intuitions of creatures who evolved on the surface of a mid-sized planet. Our nervous systems were shaped by natural selection to help us survive, not to accurately perceive the deep mechanics of space-time, and the universe carries no obligation to conform to what feels reasonable to us. What Einstein's special theory of relativity established in 1905 is that the rate at which time passes depends on how fast you are moving through space, and not in a vague philosophical way, but in a precise, measurable, physical way that holds up under repeated experimental scrutiny. Move faster through space, and time slows down for you relative to observers who are stationary, not as a feeling, not as a cognitive distortion, but as an actual physical fact that atomic clocks confirm every time the experiment is run. Hermann Minkowski, who had been Einstein's professor in Zurich, took this further in 1908 when he reformulated the whole picture mathematically, showing that space and time are not two separate things, but two faces of a single four-dimensional structure called space-time. Every object in the universe moves through space-time constantly, and the faster it moves through the spatial dimensions, the more slowly it moves through the time dimension. Slow your movement through space to nearly nothing, and time moves as fast as it ever does for you. Approach the speed of light, and time slows towards stopping. The Hoeffele-Keating experiment in 1971, which put 4 cesium atomic clocks on commercial flights around the world and compared them to identical clocks that stayed on the ground, confirmed Einstein's prediction to a precision that closed all reasonable debate. 66 years after the theory, the clocks told the same story the mathematics had predicted. What makes this stranger still is where that confirmation ended up. GPS satellites orbiting Earth must account for 2 separate relativistic effects: the time dilation produced by their velocity and the time dilation produced by the difference in gravitational strength between orbit and the surface. And without those corrections built into every calculation, the navigation error would accumulate to roughly 7 miles per day. The technology works because the physics is real. And the physics that makes your navigation possible was first developed not to help you find a coffee shop, but to improve the targeting accuracy of intercontinental ballistic missiles during the Cold War. The equations describing the bending of time were weaponized before they were made available to the general public. And every time you ask your phone for directions, you are relying simultaneously on the truth of Einstein's relativity and on the particular history of nuclear deterrence. General relativity, completed in 1915, extended the picture further by showing that gravity is not a force transmitted across space the way Newton conceived it, but a curvature of space-time caused by the presence of mass. The sun does not reach across empty space to pull Earth toward it. Instead, the sun's mass warps the geometry of space-time in its vicinity, and Earth follows the natural curves of that warped geometry the way a marble follows the curve of a bowl. And just as velocity slows time, gravity does too, with stronger gravitational fields producing slower time, which means time at Earth's surface moves more slowly than time at satellite altitude. Near something as dense as a neutron star, the effect becomes severe. At the event horizon of a black hole, the boundary beyond which nothing can escape, time, as measured by a distant observer, appears to stop completely, with 2 observers watching the same event and experiencing it as happening at entirely different rates. That is not a thought experiment or a metaphor. It is what the equations of general relativity describe, confirmed by every observation we have made of objects massive enough to produce the effect. Now comes the part that most people miss entirely. The part that sits underneath everything else and explains the most basic feature of daily experience. Time has a direction. The past stays in the past. The future has not happened yet, and nothing in ordinary experience suggests that arrangement could be any other way. You stir cream into coffee, and the mixing happens, and no version of waiting or stirring backward ever reverses it. Glass shatters and stays shattered. The direction feels so absolute that questioning it seems almost absurd. And yet, quantum mechanics, electromagnetism, and Newton's laws of motion all work identically, whether you run them forward or backward in time. The mathematics of physics at the particle level does not insist that time move in any particular direction. The arrow exists, but the equations that govern individual particles do not explain it. The explanation lives in what physicists call the second law of thermodynamics, which states that entropy, the measure of how many different arrangements a system's components could occupy, never decreases in a closed system. The Austrian physicist Ludwig Boltzmann spent the second half of the 19th century working out what this means at the level of individual atoms, demonstrating that entropy is not a force pushing the universe toward disorder, but a statistical fact about probability. There are vastly more disordered arrangements available to any system than ordered ones, which means disorder is not something the universe moves toward because it is attracted to it, but something it falls into because the alternatives are so much rarer. The scientific establishment of Boltzmann's era rejected his conclusions, and he died without seeing them accepted. But the physics he worked out is now the foundation of the field, and the implications run all the way down to the origin of time's direction itself. Time's arrow points toward increasing entropy because the universe began at the moment of the Big Bang in a state of extraordinarily low entropy, of improbable order, and has been moving toward the more probable disordered arrangements ever since, each step in that direction corresponding to what we experience as the forward passage of time. What nobody can currently explain, and what sits at the unresolved center of physics, is why the Big Bang produced such a low entropy initial state to begin with. The description of what happened in the earliest moments of the universe is detailed and well supported by observation. The explanation for why those first moments were so improbably ordered, the reason time has a direction at all, remains an open question that no existing theory fully resolves. The most basic feature of your experience, the sense that time moves from yesterday toward tomorrow and not the other way around, ultimately traces back to an initial condition that science can describe but cannot yet explain. Consider what that means for what you actually are. The atoms making up your body were forged inside stars that burned out and exploded billions of years before Earth existed, scattering calcium and iron and oxygen across space to eventually coalesce into planets and oceans and living things. The iron carrying oxygen through your blood right now was produced inside a star, distributed across the galaxy in a stellar explosion, gathered into the solar nebula that formed this planet, and cycled through billions of years of geological and biological history before ending up in you. We are, in the most literal sense available, material that stars made and the universe recycled, organized by 3.5 billion years of biological evolution into a form capable of reflecting on its own origins. That capacity for reflection, the consciousness you are using right now to follow this argument, is itself a product of the same deep time. Natural selection on the African savanna shaped a brain designed to find food, avoid predators, and navigate social groups, and that brain, without any modification to its basic architecture, turned out to be capable of working out the curvature of space-time and the statistical basis of entropy. The Voyager 1 spacecraft, launched in 1977 and now traveling through interstellar space beyond the boundary of our solar system, was built and aimed and sent outward by creatures who have existed for 10 seconds on the cosmic calendar. The temptation is to look at that 10 seconds against the backdrop of 13.8 billion years and feel the smallness of it, but that reaction misses what the number actually represents. For almost the entirety of cosmic history, the universe contained no mechanism for knowing itself. Galaxies formed and stars burned and planetary systems came and went with nothing anywhere capable of noticing that any of it was happening. And then, on one ordinary planet orbiting one ordinary star, matter arranged itself into beings who could look outward and inward simultaneously, who could reconstruct the history of the cosmos from the light arriving at their eyes, and who could trace the arrow of time back to the improbable, ordered state that started everything. That is not a small thing hidden inside 10 seconds. That is what 10 seconds turned out to make possible. When the common picture of time collapses, when you stop treating it as a steady background current and start seeing it as something that bends under velocity and warps under gravity and flows at different rates in different places and points in one direction only because of a statistical improbability baked into the universe's origin, what remains is something far stranger and more interesting than what you started with. The next time you stand outside on a clear night and look up at the stars, you are not seeing the sky as it is right now. You are seeing Rigel as it appeared in 1160, Messier 31 as it appeared 2.5 million years ago, dozens of other stars from dozens of other eras, all assembled by the coincidence of their light arriving simultaneously into what appears to be a single present moment. You are standing in the present, bathed in the past, made from material older than this planet, possessed of a mind that evolution never designed for this purpose, but that works anyway, looking out into depths you were never built to comprehend, and comprehending them all the same. You are not standing outside of time, watching it move past you from a safe distance. Time is the river, and you are the water.